Okay, so thanks everyone for joining today. It's our great pleasure to have Florian Dorfler speak in our seminar series today. Florian is a professor at Automatic Control Lab at ETH Zurich. He is widely recognized for his contributions at the intersection of control, system theory, optimization, and learning, with some focus on network systems and data-driven settings and power systems. He completed his PhD from UCSB, and he was briefly a faculty at UCLA before moving to ETH. His research has been recognized by many prestigious awards, including the IFAC Manfred Thoma Medal, European Control Award, and more recently Rossler Prize, which is ETH Zurich's highest scientific honor across all disciplines. So that's quite cool. His work has been recognized very frequently in the form of best paper awards at several top venues in conferences and journals in controls, power systems, ML, etc. Some of you may also know him that he serves as a senior editor of Automatica and also a council member of European Control Association. So it's our pleasure, Florian, to have you in the seminar series. And today, Florian is going to talk about the LQR learning pipelines. Just one quick logistics thing before we start. If you have any questions, please feel free to post it on Zoom chat, and maybe we can aggregate all the questions at the and have a discussion towards the end. So, Florian, floor is all yours.
Perfect. Thank you very much for the kind introduction. And thank you all for joining online and wherever you are. I know online talks are not the most exciting ones, but I'll try to keep them entertaining. So I will talk about LQR learning pipelines because I discovered that there's quite a large gap between reinforcement learning and classical adaptive control that I want to fill here. The spirit of seminar series is multi-agent. So far we only captured the single agent case, but I believe that's already exciting enough. But we're working on the multi-agent scenario. Good. Let's get started. Quick acknowledgement to my collaborators. This has been done by collaborators in 3 countries, mostly by my postdoc Feidan Chao, former postdoc Limin Huang, Alessandro Chiuso, and Niklas Persson, as well as some others. Okay, I want to kick things off by sharing some perspectives on data-driven control. I suppose all of you are listening that are probably familiar with the field overall, but let me share some thoughts. So the history is very long and rich. I can trace it back to the auto-tuners, auto-tune PID controls in the 70s, which are now, million times, distributed all over industry. But the history is also quite vast and fragmented, at least between 2 fields, adaptive control and reinforcement learning, RL. Okay. There have been, of course, various overlaps. And, there's quite a famous paper, at least a paper with a famous title. Much of the paper itself is famous, but inventors of reinforcement learning that said reinforcement learning itself is direct adaptive control. So definitely these 2 fields have a common root, namely they both start off from dynamic programming. That is, you want to solve a control problem by taking an optimization perspective. And have been some early crossovers about 10 to 20 years ago under the names of neurodynamic programming, approximate dynamic programming, or adaptive dynamic programming. And there are great papers that came out, books, but then it never took off and it became mainstream. And I think the reason is mostly because there's just a big culture gap between these communities. Let me quickly elaborate. So in reinforcement learning, you look essentially at the world as an online optimization problem that you have to solve. Whereas from the control side, you look at everything as a stabilization problem. When dealing with uncertainty, there's also a culture gap. Are you robust versus do you embrace optimism? When it comes to what you call a solution to a problem, classical adaptive control would seek, pen and paper results, whereas modern reinforcement learning goes the computational path. And of course, it depends what you want. You care about theoretical certificates or empirical studies. And so because of this culture gaps, this gap has never been closed. But today, of course, there's a new generation at work and there's plenty of cross-fertilization, and I hope we can bridge that gap. So let me now shine a spotlight on data-driven design pipelines. So you are a designer of an algorithm or an agent or controller, depending which community you come from, we give it different names. So you're the brain. You interface with a process, a plant, a system that you don't have a good description of. So it's just called a black box. And the first choice you have is, do you go model-based, do you build a model, or do you just adhere to the data you've seen? And in more classic terminologies are called the indirect and direct approaches. So in the indirect model-based approach, you use the data that you observe to identify a model as well as an uncertainty estimate, and then you do control design based on that model. Whereas in the direct approach, we essentially just adhere to the data you've seen, and there's various keywords, mostly from the distant past, like model-free adaptive control, model reference adaptive control, and so on. But there's an entire community working on that as well. There's other classifications on the control design pipeline, namely whether the algorithm itself is offline or online. So an offline algorithm, also called episodic, would work with batch data. So you collect a batch of data. From this, you design your policy, you roll out the policy, you collect new data, and you repeat in episodes. If that algorithm itself is online and that feedback loop between data you collect and redesign the algorithm is in real time, then you call this normally adaptive. So you measure something, you update your policy, act on the system, and you repeat immediately. Here's just some keywords people associate with different pipelines. And there have been well-documented trade-offs, going back to whatever, 20, 30 years ago. If you even open up the old box, people discussed about the pros and cons of all of this. This is sort of fairly well understood. So it depends on what your goal is. Is it an optimal design versus a robust design? Do you want a modular or an end-to-end approach and of course, the different terms of computational complexity, sample complexity, and how approachable they are from a theory perspective. The gold standard, if it exists, would be the following. Ideally, you want to have an algorithm that is adaptive, that is, it is online. Okay? It should be optimal, at the same time robust, cheaply implementable with recursive algorithm, and of course, tractable. And most people would agree that the direct approach is superior to the indirect approach. That is, if you can go without a model, you should go without, reason being mostly uncertainty propagation. But you already see, I call this the gold standard. That means it's likely, not, and never achievable. Okay, let's see if we can study these different pipelines better on, the basic example, the most basic example, the cornerstone of automatic control, the one you probably all learned in bachelor courses, which is the LQR, the linear quadratic regulator. So the setup is very simple. We have a plant in discrete time. So state is x, x plus is ax plus bu, a linear plant, subject to disturbance w. You close a linear feedback loop, u is kx with a linear gain. And the performance output you care about is this z, which is property that z squared is a quadratic constant. It's x transpose qx plus u transpose ru. And this sort of the benchmark also of reinforcement learning, and probably the only really analyzable case of reinforcement learning where you can say very crisp results. Here would be the mathematical problem formulation. You minimize a long-term average quadratic cost subject to the dynamics and your linear policy. So what you do, you have a cost at any point in time, quadratic in x, quadratic in u, with some mating matrices q and r. You take the long-term average of this cost, and you take an expectation with respect to disturbance, assuming it to be stochastic. Subject to your linear dynamics and subject to your policy also being linear. Okay, that's the classical problem in both control and reinforcement learning. And of course, people explored this problem from all possible angles, including the four I showed you, namely episodic, adaptive, direct, and indirect. And you would think everything that could be said has been said about this problem probably already a good 40, 50 years ago. Well, to my surprise, people did not cover certain aspects, and now I understand why. For instance, there has not been any direct and adaptive LQR approach to this. Can you solve the LQR problem adaptively, so in real time, learning the dynamics, and direct without ever employing a model? Okay. The reason why this has never been developed is, well, at classical adaptive control, people didn't care about optimality, so they didn't pursue this particular problem setting. Also, they told me, the old generation told me they did not find the right error coordinates to stabilize. So it was just not an interesting problem to them. Conversely, in the reinforcement learning side, there are, of course, many RL people that have studied all sorts of variations of adaptive learning programming and so on that solve this type of problem. But all the certificates that have ever been provided in this vast literature are actually only on the algorithmic side. That is, they would show certain types of policy iterations or so would converge to the optimal solution, but there's no single statement about the closed loop. That is, while you keep on updating your policy, are you actually stable? Will you converge? Will you be bounded? What's the closed loop cost? In fact, all papers you find on the RL side are typically just on the algorithmic aspects, on the policy, and then not on the stability aspects. But that has changed, I think, maybe 2 years ago, and then people now also from both sides look into both the optimality and the closed loop properties. But there are these research gaps which surprisingly have been overlooked for many decades. So today I want to revisit this rather old problems with a new perspective. The new perspective is I will employ a very abstract branch of system theory called behavioral system theory. Behavioral system theory is due to a Dutch mathematician called Jan Willems. Belgian mathematician. And he described the system very abstractly, just as a set of trajectories. Okay, it's just a set of trajectories, say, in the space of input and output sequences that you can represent by classical models or by data. So for instance, you would say a linear system is just a subspace in the space trajectories, and you can characterize as you wish, for instance, only by data. And I will use a particular representation of these set of trajectories, which goes through sample covariances, which have recently become popular. And there's been a plenary talk at the CDC 2 years ago. Maybe you attended it, Anders Ranzer. So this is one of the new perspectives I will take. And the other one is on the adaptation side. So I guess every new kid on the block, everybody that has been trained in the last, say, 5 to 10 years, if I ask them, you get a new data point, what you would do? You would probably all give me the same answer. Well, you go down the gradient, right? I mean, stochastic gradient descent is what drives the entire AI revolution. Well, it turns out this idea of going down the gradient, that is, take a gradient step in policy space to minimize your control objective, has not been pursued at all, ever, really, in the either optimal or adaptive control literature until very recently. That is the obvious thing of saying, K plus, the policy at next time step is the old policy, minus step size times the gradient of the cost, which seems very, very obvious. So policy gradient descent is a rather new thing in the control world. I guess back 5 years ago, people only rediscovered that type of thing. So we'll revisit these problems using these two toolkits. Okay, so here's the setup. So I'll just present a few, a little bit of problem setup. I'll further open it up. I'll talk about different learning pipelines, how you can solve that problem. And I'll present you closed loop results, both in terms of stability, optimality, and robustness. And I'll illustrate things for you with different case studies, both numerical, robotics, flights, and power system. All right, so look into the problem setup a little more in detail. Here's again the LQR problem. You've already seen that block diagram, a linear system with a disturbance W and linear feedback policy. I care about finding the optimum policy, minimizing the linear quadratic cost here on the left-hand side, this one. Typically, this is not how you solve that problem. The way we rewrite that problem normally in the language of controls is in the language of LMIs or semi-definite programming or so. More formally, what would you do? You would actually change variables, namely you would introduce a state covariance variable sigma, which is, I guess, in this case, the long-term average of x times x transpose. That's just the state covariance, also called the controllability gramian. And then you would rewrite things in this language of state covariance. That's very classical, has been done decades ago, and probably you recognize the formulas, because then you could rewrite the anti-problem as follows. So you write, instead of x transpose qx, you write the trace of q times sigma. So sigma is essentially xx transposed. And here you write, instead of the u, you write kx. And again, that here then trace is k transpose rk sigma. Okay. And now the problem is formulated in terms of matrices, where sigma is a positive definite matrix. The way this sigma is updated, it just follows the closed loop Lyapunov equation. So sigma is identity, and then a plus bk sigma and a plus bk. Okay, this is normally how we solve this type of LQR problems. In terms of algorithmics, you can easily reformulate this as a convex program after change of variables. You can write this as a semi-definite program or as a discrete Riccati equation, which you can then attack with your favorite methods, very classical interior point contraction methods, or some policy evaluation, policy improvement, like a Heuer type algorithm. Okay, all very classical and has been done and around for decades. All right. So let's take a data-centric perspective. Let's say we don't have a model. We need to construct a model from data. So maybe look at this block diagram. So this would be my system. And now I collect some time series. So I'll collect the state time series, x0, from time x0 until time t-1. So that's a vector or a matrix with t columns and number of states, number of rows, n. I also look at this time series one time step shifted. I call this x1. So now it goes from time 1 until time t. I have the input time series u0 until ut-1. And let's assume for now also would have the disturbance time series. I would know the w disturbance sequence. Then all these data matrices would be just related by my dynamic equation. So x1 is x0 plus bu0 plus w0. Now, of course, what makes the problem fun is that your disturbance, essentially, for instance, Gaussian noise is unknown, and you cannot perfectly reconstruct this. And so you need to estimate your model. To estimate the model, whatever approach you take, it turns out a necessary condition, say for instance, a least square problem, but any other approaches that need to assume the data is persistently exciting. That is, these two matrices, when you stack them on top of each other, needs to have full rank. Okay, so the rank of u0, x0 is n plus n. Under these assumptions, you can solve any identification, also optimal control problem. So here's the classical way of doing it, called indirect and certainty-equivalence, LQR. The first thing you would do, you would first estimate your A and B. So you don't know the W. You just assume it to be 0, so certainty-equivalence. So let's say it's the mean value. And then you just minimize the residual of left and right hand side of this equation, so a least square problem. So you minimize of all b and a, x1 minus bu0 minus ax0. That's least square modification. This gives you two estimates, a hat and b hat, and with these two estimates, you go then into your model-based design pipeline. So that's the certainty-equivalence LQR design in a model-based fashion. You solve it all offline. Okay. Now, why would you not want to do this? Well, that's something that generally bugs me about people doing data-driven control, as they call it. And, it's not fun when you separate offline learning and online control. So if you solve all your problem offline and then just roll out your policy online, it's a little bit cheating in terms of this will not allow you to improve your policy online ever in case of any sort of variability, time varying nature of systems, disturbances, or nonlinearities, and you cannot simply adapt. Okay, so you don't want to go for an offline solution. You want to have an online solution to this problem. It turns out nobody ever wrote down a definition of what does it mean to be, online adaptive. Okay, the anti-adaptive control community, it's quite rich and, powerful and has been around for a long time. And whoever asked from that community, even the old guys, they would not tell me that there is a definition of adaptive control. At least there's no definition that has been universally accepted, quite surprisingly. So here's my definition. It's from a guy called George Zames, who was not an adaptive control guy. He was actually, in the other camp. They didn't like him. But he put forward a definition for adaptive control, which is very much resonating with how modern people from reinforcement learning would see this adaptation. He essentially had two monotonicity principles of adaptive control. He said, well, you interact with the system to acquire more information. So information gain has to grow over time. And you want to improve the control performance over time. That is, your controller should improve over time. You want to improve upon the best offline control, which is very much aligned with, I guess, how people in reinforcement learning would see this and notions of regret and so on. It turns out in the adaptive control community, his definitions did not fly because they were focused mostly on stability problems, a separate story. So a desired adaptive solution for such a problem would be, we want to have an online algorithm, so non-episodic, non-batch, that should work with closed loop data. It should have a recursive implementation and, ideally direct, but, if you cannot get that, we also would settle for indirect. So that's what we're after now in this talk. And our strategy, how to best improve the policy online is, we take the naive or maybe natural approach, say, let's just go down the gradient. With every data set we get, we take another gradient step and keep on updating, which literally any new kid on the block nowadays would do this, but has not been considered in the last decades. So here's the block diagram, what we want to do. So here's our LQR problem, linear dynamics, linear policy. And I want to do now is the following. I will take my latest measurements to update my policy. So I also simultaneously will do a gradient descent on the policy. So k plus is k minus eta times the gradient of my LQR cost as a function of k. It turns out on top of this, I will likely have to continuously inject some probing noise into my input to just make sure I have persistent excitation. This, my data matrices will always be full rank so that I can, calculate gradients. Okay. So this is what I want to explore today. This seems rather obvious, almost naive. We think it's not worth thinking about that. It must have been solved a while ago. Turns out it hasn't. Let me tell you what the challenges are. On the algorithmic side, the challenge is how the hell would you actually compute the gradient of the long-term average cost with respect to the policy parameters? How would you just cheaply, recursively with one data sample, the next one? So the direct and indirect, will this converge? On the control side, in terms of the closed loop, it's not clear that you get stability by doing that. It's not clear this will be a robust algorithm, and maybe also not even clear this will actually converge to any optimal solution. Yes, these are the questions we want to pursue today. Good. Let me give you a preview before I tell you how we do this. Let me just show it how it works. So here's an autonomous bicycle. So a bicycle is equipped with plenty of sensing actuation, so it could actually ride by itself. It's part of a project from my colleagues in Sweden that they have with Volvo, where they want to have autonomous bicycles that would literally ride by themselves. What we do is the following. So we have our autonomous bike here. That's this guy. We take a low fidelity model, so not a good one, just a few states, and we do a feedback linearization, so we cancel the main nonlinearities in a model-based fashion. Of course, we only do this with a very coarse model. And then around this entire loop, we strap around our gradient descent on the LQR policy. So here's sort of our adaptive control. So we solve the optimal control problem and keep on updating the policy via gradient steps. So this is what comes out. Let's see if this runs. So you can see the bicycle nicely riding here. It would actually work quite wonderfully. It would stabilize itself. And you can see in the plots on the right, maybe the most important one to look at is on the lower right. You see the control gains, they change over time, but eventually they would converge to the optimal values of this LQR cost. So long story short, it works. You can make this work even on non-trivial, even open loop unstable systems. Good. Now let's see how we do this. Let's first look on to the algorithmic side. How can you compute the gradient in a very cheap recursive way? And here's sort of the algorithmic roadmap. I'll give you a bunch of different options that I walk through you. So all these algorithms, let me start with the simplest one, namely, let's go down the indirect route. This we collect our data. From the data, we identify a model, and from the model, we compute the gradient. Okay, so let's see, we get our data, we do a least squares, recursive least squares, and then how do we compute the gradient? So let's look at this LQR optimization landscape. Okay. So you may remember from your control course that this sigma here, which is called a Lyapunov matrix or controllability Gramian, you can actually solve this in closed form. The unique solution sigma to this entire equation, it's given by the matrix of the system times to the power k and the sum of all k from 0 to infinity. So that's a unique closed form solution, actually. So you could already remove the sigma and just think about this entire problem as a function j of k. All right. So it turns out when you plot this entire cost function as a function of the control gain, so here for a two-dimensional system by some colleagues in China, you see this looks quite well behaved. It's like, yeah, that looks nice. You should be able to do something like gradient descent on that. But don't fool yourself by low-dimensional versions. In general, this is a nasty problem. You can easily show this is not convex. Okay? But what are the properties you have in this problem? So it turns out that the cost function is actually differentiable. That is, within the set of all stabilizing control gains, you can compute a gradient. The gradient will be given by this formula. This formula will depend on your A and B matrices. It will depend on the sigma, your Lyapunov matrix here, the controllability Gramian. And it will depend on another variable P. P is solved by this equation, which you don't look into the details so closely. It's also a Lyapunov equation. It's just a closed loop observability Gramian. This, if you give an A and B and the Gramians, both controllability and observability, you could actually compute the gradient. And that's a result that has been known actually already in the 1970s. There have been papers on That's the gradient of the LQR. So it's nothing terribly new. However, people did not really make use of this because they didn't perceive this as useful for this highly complicated problem. It was only actually in 2019 that a group around Mario Fasel proved that, hey, this actually may work, because they showed something on the optimization landscape. This entire problem is recursive. That is, your level sets are nicely compact on a set of stabilizing gains. The problem is smooth, so you have a bounded Hessian matrix. And you have a gradient dominance property. This J of K is upper bounded by your optimal control cost plus a constant times gradient squared. Okay. And it turns out these properties are enough to actually show that gradient descent, when properly stabilized, properly initialized for small enough step size, would converge, which was the main contribution of this one in 2019, and they started or revived the entire literature. So here's the result. So here's your, again, your optimization problem, minimize the cost of K, and then they showed for K0 that is stabilizing. So if your initial iterate is stabilizing, you pick a small enough step size, then just a standard vanilla gradient descent, K plus is K minus eta times the gradient of the cost, would actually converge with a linear rate to the globally optimal solution of this LQR problem. And that was proved in 2019, and ever since many papers. Here just so a few of them. I refer to that survey if you want to have more knowledge on that. All right, that's good. So here is how you could construct an algorithmic pipeline with this result. So you get your data. From the data, you estimate your matrices A hat and B hat. So you can use recursive least squares to have a cheap update. Then you do the gradient descent. And as you see now, the crux of the gradient descent will actually compute the gradient. To compute the gradient, you need your estimates of the matrices and the resulting closely prime sensitive to compute. You do these steps, you actuate on the system, you get new data, you refresh, and you repeat. So you keep on doing this. And at least on the algorithmic side, you would have this type of property that the policy would converge. Nothing said here about the closed loop yet. It's just purely algorithmic, as long as the data is persistently exciting. All right, so that's the vanilla version. But there's also other versions you can take. Namely, you can do gradient descent different metrics, like natural gradient or a Newton metric, which are preferable. And let me quickly show you what they look like and why. So as you know, gradient descent can actually converge quite slow if the level sets of your cost function is very elongated, so they're not very well conditioned. This may quite slow. You rather would like to go down the straight line as if the level sets were round, like here. And you can get to the straight line if you precondition everything. So if you pre-multiply your gradient by the inverse of the Hessian matrix. This is called the Newton iteration, or Gauss-Newton gradient descent. Now, computing the inverse Hessian is, of course, very costly. And so people figured out all sorts of ways to approximate cheaply the inverse of the Hessian. Okay? And they've also done this for the LQR problem. And they showed that this actually equals a very popular reinforcement learning algorithm called Hughes algorithm, which says you iterate between evaluating a policy, improving a policy, evaluating policy, improving policy, and so on. It turns out if you do a Gauss-Newton gradient descent, you would actually essentially just alternate between policy evaluation and improvement, which is a result due to these guys here on the right. Another descent direction you can take is what is called the natural gradient, very popular in machine learning for stochastic problems. The reason is the following. Gradient descent, if you have a very non-convex optimization landscape, will take you a long way to eventually figure out a possible way to the minimum, right? So if you just always follow steepest descent in a Euclidean metric, you may go through a bunch of detours. Whereas instead, you would like to go in a direction which somewhat, gives you more variance in the objective. And that's what this natural policy gradient does, namely, it says it uses for M of K the inverse of the Fish information matrix. If you don't know what it is, it's not important. Essentially about some sort of variance of your cost function. Okay, so you go in the direction that has also the largest variance, not just downhill, but largest variance. You can also show that this, if you take the inverse Fish information matrix in front of the gradient, this for our example is just the gradient times the inverse of the state covariance. So it's very easy to evaluate. It's not very expensive. Okay, you can easily compute this thing. So these are a little more algorithmically favorable ways of doing gradient descent. But they're still indirect. You would still have to compute everything based on the model, and the model you have to learn. So let me show you how we do this without a model. how can you compute gradients without a model? And that's where it connects to, I guess, more classic or more contemporary reinforcement learning. So why would you even go direct? So why would you go model-free? Why would you compute policy gradients the model-free way? Because we just did certainty-equivalence so far, right? We completely neglected uncertainty. What you should really do, we should take the uncertainty to account and propagate the uncertainty from the data to the system modification to the gradient computation. But this is, of course, very hard, not easy. And whatever you do based on the model will suffer from a bias error. You a priori chose a model class and it can be arbitrarily wrong. For instance, choosing a wrong order of a system. Okay, so often direct is preferred. So here's how you do it with classic contemporary reinforcement learning. You use essentially model-free zeroth order methods. You would construct the gradient as probably learned in high school. So the derivative of a function is you evaluate the function left, you evaluate the right, you take the difference, divide it by 2. That's probably what you learn. Finite difference method to approximate, or that will converge the derivative. So we do something similar here. So we take a random perturbation, u, a random variable from a uniform distribution. We go to the right with magnitude r. We go to the left with magnitude r, and we divide everything by r squared times the dimension. Okay, and you can show that this way of constructing a gradient in expectation will actually give it a gradient. So far, so good. Now, on a computer, you cannot construct random variables. So you need to approximate this entire thing by samples and do sample average. So you need a lot of them. But the real crux when you want to implement this is, just evaluating cost function, evaluating j of k plus a perturbation. Think the cost function is the long-term average. So you need to, in principle, run this to infinity. To just evaluate it. And of course, you don't have to run to infinity. Long enough is good enough. You don't have to take infinite many variables. But you can do all the scaling laws. And let me just give you the numbers. So say we have a fourth order system. We want to solve it to 1% optimality using model-free policy gradient methods. To 1% optimality, relative performance gap. It turns out what I need is trajectories which are of length 100 samples, so 100 time steps. And to get within 1% optimality, I will need 142,000 of these trajectories. That is in total, I need 10 to the 7 data samples from my system for a fourth order system to get within 1% optimality, which already tells you this is why reinforcement learning does not work on physical systems. It only works when you have a simulator that you can query infinitely often, right? So that's why nobody does reinforcement learning on the real experiment, because it wouldn't work. So you need a simulator that you can query infinitely often. So certainly it's not practical if you want to do online adaptation of a real physical system. So it's not useful for adaptive control at all. So takeaways, direct policy gradient methods, whatever you use, using zeroth order approximations are very inefficient. They're episodic because you need to construct all these long trajectories and sample paths, and they're essentially completely useless unless you have a perfect simulator. And if you have a perfect simulator, you don't need to do anything with a black box anyway. So it's a little bit an ill-posed problem. So we can neglect monsters, right? In fact, what we'll do now, we'll call another way of thinking to the rescue, and those are sample covariance parameterization that allow us to compute the gradients without running 10 to the 7 samples. So let's again look into this block diagram. I will neglect noise for now. I'll bring the noise back in 2 or 3 slides. Let's keep it clean for now for simplicity. So we have our time series of inputs, of states. We have a time series of successor states, x0 and x1. We have a time series of inputs. And we know if we had the ground truth model, these 2 time series are 3 times related by the model. So x1 is ax0 plus bu0. Now let me use the data and construct some sample covariances. So I take the input state vector and I construct the empirical covariance matrix. So this vector times its transpose divided by the length of the time series 1 over t, which is a positive definite matrix. Why positive definite? Because I assume the time series is persistently exciting. I also construct a covariance with the successor states, so the past input state and the next state. That's another covariance. I call this one lambda plus. And now let me do some very simple algebraic manipulations. In particular, the first one we do is the following. This matrix here is full rank. It's positive definite. That is, any other matrix of the right dimension will live in its image. In particular, the matrix of the unknown control policy, I don't know it, K, and identity matrix will live in the image of this one. In particular, mathematical state will be for any control policy you choose, there exists another variable v, so that K identity is the sample covariance times v. All right, sure, yeah, but that's just linear algebra. Why is that interesting? Let me further massage the closed loop equation, and you'll see in a second why. So I have my a plus bk. That's what I care about. Remember, in all these control formulations of the LQR problem, everything is parameterized by a plus bk. And what I want to do now is replace a plus bk by purely data-driven parameterization. So I can replace a plus bk by b times k and ai. So far, so good. Notice ki is exactly the green box. So I'll pull down the green box here, and I get ba times the sample covariance times a new variable v. Now the first one is here b times u0, and the second one is ax0, which is exactly the right-hand side of your model equations. So I can replace this entire thing now by the success state x1. So this is just now an x1 times, and that's another covariance from this up here. So you don't have to follow every single symbol here. I just want to show you this is all very basic, trivial linear algebra. So I replace this everything now by my sample covariance lambda plus. Now, why is this any interesting? These are just linear algebra tricks. The takeaway is the following. Whatever control design formulation you have, using Riccati equation, using LMIs, or whatever other sophisticated algorithms, they all have as main variable the a plus bk. And these substitutions will allow you to replace a plus bk by data matrices. Particularly the new variable v, the v is determined from the green box. Okay, so instead of k, you work with v. And then if you just, the covariance times v, or the covariance with successor state. The main takeaway is the following. You can replace all your optimal control formulation that you've ever seen for linear systems by raw data, by sample covariances. And now just work with raw data parameterizations and completely sidestep, the system application if you want to. It's just another parameterization in terms of data. Great. So takeaway, we can reparameterize our problems in sample covariance matrices. Details are not so important, just trust me, you can. Aside, a lot of people in the last 2-3 years have discovered sample covariance is an extremely useful parameterization for all sorts of control problems. Here's just a few references I stumbled over, so they're quite useful, also in the classical literature. So they're definitely on the rise. They're related to other parameterization that people use, like trajectory matrices. Maybe some of you have seen the work by De Persis and Tesi, but they have some advantages over there that I can comment on offline. So you can parameterize everything now in terms of these covariance matrices. So here we have a covariance, here we have a covariance, lambda and lambda plus. Okay, instead of writing this problem as you've written before, I just rewrite it like this. That is, instead of a plus bk, I have my covariance here, and I have a new optimization variable v. It doesn't change anything. I can still do gradient descent. So I could still, everything do analogously. So now this problem is written in v coordinates. I have an extra linear constraint here from the parameterization, but everything else is the same. I can do policy gradient descent. So I do my policy gradient descent now in v space. Same as before. The only difference is I have to have here a little projection that just makes sure that this linear constraint is satisfied. It's just a linear matrix projection. Again, everything converges. Here's, by the way, the same fourth order system for which reinforcement learning type 0th order algorithms will use 10 to the 7 samples, like a lot, 10 to the 7. And now I can solve the same problem using now only 6 samples. Okay, I got from 10 to the 7 to 6 samples, because 6 samples are enough for me to compute the policy gradient actually at all times. So I only need 6 samples to do this, and I get from 10 to the 7 to 6, and now suddenly this actually becomes useful by going to this parameterization, not doing 0th order methods. And that we want to do this online now. Okay, so that's our strategy how to do this online. Okay, just parameterize things in covariance matrices. Just a few facts. Is that everything we do is just a reparameterization in terms of data matrices, and we do policy gradients and the new coordinates. The first fact is, we can recover in original k coordinates if we do, again, a gradient descent, with the only difference that there's a scaling matrix before the gradient that now will depend on your data matrices. But you can lift over all converged result people have proved into this new direct parameterization. Okay. Again, details are important. It's just essentially a positive matrix in front. Another interesting fact is that You can also do natural gradient descent these coordinates, and that's actually coordinate invariant. But as you can actually show, if you do the natural gradient descent in this covariance parameterization, you recover the model-based natural gradient descent one-to-one. It's coordinate invariant, which is also a fun fact. So again, you can lift away all results people have proved from the model-based case to this direct parameterization. And I don't need to reprove things after this two facts. Okay. So on the algorithmic side, we can do all of this. So we can do the direct gradient descent. It turns out we need to count the noise. Okay. Actually, in both variations, but it's easier for me to explain to you what the robust gradient is if you had noise here. So notice in the real setup, we have here another matrix W that accounts for noise process. And we don't know this W, right? We computed the gradient neglecting the W, the noise time series of the noise. If you were to repeat all these algebraic tricks I told you about, how you can go from the model-based parameterization to the covariance parameterization, if you were to include the W0, so the noise matrix, you would not get that A plus BK is a covariance matrix times V. It would be a covariance matrix minus something that depends on the noise, which is this term. And we completely neglected that. And of course, now, when you have a noisy data set and the system driven by noise, the gradient that was computed without the noise may actually not be stabilizing. You get an issue, right? That's also the model-based case. So in fact, what you need to do to counter the fact is someone need to close the gap between these two parameterizations. So you could look into the two Lyapunov equations that were computed with and without noise. Just give you the conceptual argument. These two Lyapunov equations would look very similar. They would only be different up to one term, which looks like this, which depends on your optimization variable, covariance matrix, and so on. So you can compute the difference of the Lyapunov equations. If you want the system to be stabilizing, computed from the noiseless gradient, also be stabilized for the gradient that would be computed from the noise data, you need to minimize the difference of the Lyapunov equation, which suggests, and I know this is very high level, a regularization term that says the following: so don't minimize the cost J of V, minimize J of V plus some coefficient lambda times the gap between the two Lyapunov equations. Okay, I know this is very conceptual, but this is what you should do to also counter noise, just a regularized cost function, which you can express either in V or K coordinates. It's not so important. So let me show you how this works. So let's say we have now 100 different samples from our problem, and we see how often it will be stabilizing. If I set lambda 0, so I don't regularize, then only 90% of the times that I compute actually my controls from the data would actually give me a stabilizing control, because the other corrupt noise may not actually give a stabilizing control. Once you start regularizing, that is, you increase the lambda, it doesn't have to go much, just to say 10 to the minus 1 or so. You actually go up to 100% of the controllers being stabilizing, which is great. So it gives you robustification. It turns out also in closed loop cost, it will give you a better performance, which is nice. We didn't aim for that. There's some more benefits, like give you algorithmic advantages. I'll not talk about that. And you can shrink the regularizer as your data grows. I will also not talk about that. But takeaway is maybe the following. If you do not regularize, then noisy data may actually not give you stabilizing controls. So you need to regularize things suitably. The main takeaway. Details you can look up. So I told you everything aside from the closed loop results. Namely, we just looked at the algorithmic side, but what happens in closed loop, right? So we have this block diagram. We have our LQR problem, linear feedback law, this one. And now we keep on adapting the policy using policy gradient descent. So you do something like this. K plus is K minus a step size times the gradient. Maybe some pre-scaling matrix M, which could be, inverse Hessian. It could be inverse Fisher information matrix M. It could do any of the previous algorithms, direct, indirect, or whatever. And I'd like to understand, does this converge? Now, it turns out on the algorithmic side, you can always now show that these types of gradient descent laws will converge. So every K of T is stabilizing along that sequence. The cost function will decrease. So what should happen, right? You wonder, are you just making a lot of fuss here? Surely everything should converge because this converges. You get stability and optimality. It turns out, no, not really. Why is that? It's a switch system. Every time the gain is stabilizing, every time your closed loop is a stable matrix if you want so, but it's a different stable matrix at any point in time. So you switch between a sequence of stable systems, which does not imply that the overall system is stable. I can create arbitrarily many counterexamples in this entire field called switch systems that is all about that. Look up the keyword that shows spectral radius. So long story short, this is not stabilizing, not converging, not optimal, anything, unless you do something about it. You need to make some assumptions on the problem. Okay. To show you the main result we have in the closed loop, I need to quickly review the information metric. So recall that this guy same said, one key feature of adaptive control is they learn over time. Information is increasing. Okay, so I need to tell you what I mean by information. So what's my dirt effect? What's my noise signal? Essentially, it's my noise covariance. And I say, let me make an assumption. The noise covariance is bounded. Noise covariance is less than delta squared. That's my noise measurement. What's my metric on signal? I assume I have persistent excitation. That is, I keep on here injecting some probing noise. So my data is always persistently exciting, full rank. And I assume that my state covariance matrix, okay, is lower bounded by some gamma squared, the lowest singular value. Okay, so you assume that's your signal metric. And then your signal to noise ratio, your SNR, is just the ratio of essentially a state covariance divided by the noise covariance. Let's quickly do some sanity check. Say the following: if your noise, say, instance, would be Gaussian in the system, and you keep on exciting the system, say with a constant excitation, you can actually compute that the signal to noise metric grows as square root of t. If your signal to noise ratio would actually be decaying, okay, so you have here, for instance, like a 1 over t term, then it turns out your signal to noise ratio will also grow as t to the 1/4. Long story short, for any practical relevance that we do this, if you just keep on exciting the system, you satisfy this monotonicity principle that information grows over time. Your SNR increases. The reason why I give you that is because the results I'll tell you about will depend on the signal to noise ratio that you have, but that's increasing over time. So here's the main result. Take literally any of the previous policy gradient descent methods, then you can make the following theorem. And then there's a lot of stuff here on the slide, and I'll go through it very slowly to unpack it. Namely, you need a stable initialization. So you need to start off with a stable control gain that is essentially the initial batch of data just to find the stabilizing control, like almost all algorithms in this field. Second, your signal to noise ratio has to be larger than a constant. You need enough signal, so enough excitation. Again, that's just happening by injecting enough probing noise. And it turns out you need the step size to be sufficiently small. It turns out if you make a step size very aggressive, then you may still converge to optimality, but you lose closed loop stability. So you actually need a sufficiently small step size. Under these assumptions, what do you get? You get the closed loop system is stable and the policy converges. In particular, you have convergence of the state with an exponential rate, and you have convergence of policy with an exponential rate, nominal. And there's a bias term, which comes A from the noise in the system, the W. So you see here, for instance, the SNR inverse scaling. And here it also comes from the probing noise, okay, because you keep on probing the system to have persistent excitation. But overall, the statement is essentially in a nutshell, choose a small enough step size, do any of the policy gradient descent methods, and you get actually closed loop stability and closed loop optimality. Which is not true, by the way, if the assumptions are violated. So I have two slides here that would actually go through the assumptions and justify them and show you how much they are in terms of rate optimum and so on. But I'll skip that. It's already late evening here, so let me skip these two and just show you some numerics towards conclusion. So first of all, let me show you convergence optimality. So here's a classical benchmark example actually coming out of Berkeley from Sarah Dean, Nick Mutney, and Ben Recht in 2019. It's a marginally unstable discrete time system. You have noise on all channels and you have full actuation. You can look into any of these algorithms and actually convince that they converge. So here's all the policy gradient descent methods. You see they all converge. And just as a benchmark, I have a one-shot method, meaning I get my data, I solve the system identification problem, and I compute the LQR problem, the optimal solution. And I assume I can do this at any point in time. That's my benchmark. It turns out I actually quite nicely follow the benchmark. I'm actually better than the benchmark. The benchmark would actually be quite, jumping around. That's maybe expected because gradient methods are more robust than computing the solution of a noisy optimization problem, so they're less sensitive. Empirically, actually serve a nice rate, slightly tighter than what we proved. Separate story, but it would work. Everything depends on the quality of your data set. So if your data set is very nice and clean and very little noise in data, all these methods would nicely converge, roughly all the same. But let's say I give you a data set that is poor, so actually there's a lot of noise on the data, then you see they may still all converge, but with a lot of variance on the way. In particular, the one-shot solution, this if you were to solve the problem at any point in time, would actually jump around quite a lot, and so would the Gauss-Newton policy gradient descent. So we conclude these methods are not very robust. Further statement, of course, doing policy gradient descent methods are computationally very efficient. I can write recursive update laws for all of these things very cheaply. And no matter which one you implement, they're all very efficient, especially extremely efficient in runtime compared to if the one-shot method, if you were to solve the problem at any point in time. Not very practical. Also, when you look at the scaling with a number of state dimensions, any sort of the policy gradient methods would have a quite nice scaling, almost irrelevant, whereas, the one-shot method would go up cubically. Not surprising, because solving these Lyapunov equations scales as n cubed. Good. I want to conclude just by showing you this works on complicated examples. I already showed you the bike. We also have examples on some aeroelastic flight. Let me just show you today my favorite example, which is on a power system, which also will connect to the multi-agent setting, hopefully in future work. It's the following. We have a big complicated system of a wind turbine. You can neglect all the details. The reason being, both the wind turbine and the power system are actually unknown to the person designing the controls. They come from proprietary companies that will not share data or models. So the control design in practice actually is black box. So you want to control that wind turbine, and you see unstable oscillations. It happens all the time. Most recently happened in Spain. You probably heard about the blackout there. And so you have to design these controls, stabilize the oscillations with a black box. What we do, we construct the state space realization from our measured data. This we just take yt minus 1, and so on as our states, and then we run policy gradient descent. Here's what it looks like. We observe an oscillation. We keep on probing the system. We collect data. If we don't do anything, you see the sustained oscillations, the gray curve. Whereas if you run the policy gradient descent, any version of that, it would nicely converge, despite the wind turbine being like a 30th order nonlinear system. Okay, so it works quite well. We're actually in the process of implementing this on real hardware right now, but I don't have the results yet. Just to show how this adapts. So say you have a change of the system parameters, say the DC voltage would change. You wouldn't see anything in the curves because nothing happens, just a change in parameters, but everything is still nice and stable, both in active and reactive power. But when there's suddenly a fault in the grid, then you see these unstable oscillations popping up. And before, you could have stabilized them, but the system has changed. And so you need to adapt your control using policy gradient descent, and you can nicely stabilize them. And then, of course, now connects to the multi-agent setting because a wind turbine is rarely alone. Now imagine you have multiple of them, and you wonder what are the interactions of all of these. I don't have answers yet. Summary, conclusion. I told you all about this block diagram today. So we do LQR control with policy gradient descent online in an adaptive way. I show you different algorithmic pipelines. You can actually show closed loop properties, stability, optimality, and a bunch of case studies, numerical and real world. There's many future works to be done, weaken the assumptions, improve the rates, go to more complex systems. And for me, an interesting question, actually, when should you adapt? Should you adapt all the time? With something like a best batch size, or should you do it some triggered fashion? All unknown. But now I'm at the end, at 50 minutes, and looking forward to your questions.
Thanks, Florian, for the fantastic